In the last video, we gave a brief introduction to linear regression. This time we'll dive into a bit more involved mathematics to build a better understanding of what's actually going on behind the scenes. As a quick recap, we had some data like you see on the left, and we wanted to fit a model to predict on new unseen data. We found out that the easiest function we can use is a linear function, and its equation is written below the plot. We can visually see that with changes in the parameters, the line shifts its intercept and slope accordingly. We also talked about how we go about finding this best fit on our data using something called a cost function. Intuitively, this was the difference between the actual value and the predicted value. We named this difference the residual, but we didn't directly aggregate. Instead, we took the square of the residuals. So how do we actually optimize this mean squared error? This is called the least squares problem, and let's dive into its solution. We know that to find the minimum or maximum of a function, we can take its derivative and equate that to 0. This point would either correspond to the minima or the maxima. Turns out that there are special kinds of functions called the convex functions for which this derivative always corresponds to the global minimum. It also turns out that the mean squared error is one such convex function. So let's solve the equation. For the two-variable linear regression we are looking at, we'll need to partially derivate the loss function with respect to omega naught and omega 1. After the partial derivations and solving for omega naught and omega 1, the solution turns out to be the equations bounded in green. As you saw before, even for two variables, the derivation became quite cumbersome. Now imagine having to do this for tens of variables instead. What we do is we use a shorthand using vector notation. This gives us a much cleaner and compact solution. Using the vector notation, instead of having all omegas as separate variables, we just place that into a single vector. Following the same rules of derivation, come to the solution x transpose x into omega hat equals x transpose y. Solving for omega hat, the solution becomes x transpose x inverse into x transpose y, and that's our closed form solution. A few things to note about this is that while it provides us a closed form solution, it isn't used. That's due to the fact that the inverse might not be possible, and secondly, because the inverse computation has a very high time complexity. So what do? In comes gradient descent, an iterative solution that approximates to the closed form solution. Think of it as evaluating what direction to move to minimize loss, taking a small step towards that, and re-evaluating. The algorithm is as follows. 1. Randomly initialize weights. 2. Repeat until a certain number of iterations are passed, or if the change in loss is less than a threshold eta. 3. Update omega by subtracting alpha times the derivative of the loss with respect to omega. And this was the mathematics behind linear regression. I hope this video equipped you with the understanding behind this model.